Ladies and gentlemen, we now move to the next session, Advanced Propulsion Systems Redefining Space Mobility. From electric propulsion and high-efficiency thrusters to reusable systems and in-space mobility architectures, propulsion technology is at the heart of the next era of space operations. This session will examine how these advances are reshaping satellite endurance, orbital maneuverability, responsiveness, and mission flexibility across commercial and strategic domains. To chair this important discussion, it's my privilege to invite on stage Dr. N. Venkatesh, Deputy Director, LPSC, ISRO, whose distinguished career in propulsion science and space systems has made a lasting impact on India's space program. We also warmly welcome our distinguished panelists on the stage, Mr.Sanket Suman, co-founder and VP RPO Inspecity, Mr. Manan Joshi, CEO Thrustworks Dynetics, Mr. Christopher Parmer, CEO and co-founder Orbitt Space. I kindly request all the panelists and our esteemed chair to please come on the stage for the session. In place of our esteemed chair, Dr. Raghupati is here to chair this important discussion on advanced propulsion systems redefining space mobility from ISRO. Let's welcome him with a huge round of applause, ladies and gentlemen. Now I hand over the stage to our esteemed chair and all our panelists for the session. Thank you.
Good afternoon, ladies and gentlemen. I would like to introduce myself. I am Raghupati, now I am a Deputy Director in Liquid Propulsion Systems Center of Indian Space Research Organization, Bangalore. We are primarily working on advanced propulsion systems for all spacecraft applications. And the title of this session's topic on advanced electric propulsion has much more relevance to all our spacecraft activities. Like revolution what has undergone in automobile sector, where people have moved from a typical petrol, gasoline based systems to electric vehicles. Spacecraft propulsion is also moving towards an electric propulsion type of setup, what is being currently followed in small satellites. The primary advantage of this movement from spacecraft in each system is the compactness of the spacecraft and low cost of spacecraft as well as low launch cost. Typically, spacecrafts have been made mobile using chemical propulsion systems, but now it is being taken over by electric propulsion system in a big way. And that is going to stay forever. And on this interaction, we will definitely like to hear from our startups and friends from different entities who are working on electric propulsion or other advanced technologies. What will be the mainstay of spacecraft mobility? A little bit of touch on spacecraft mobility, even though the spacecrafts are put into orbit at particular orbit levels. There are some situations where spacecrafts have to be maneuvered to meet its objectives. And in that sector, now electric propulsion is going to play a bigger role. And ISRO has already taken a great step in this direction by introducing spacecraft electric propulsions in GSAT 4, GSAT 9, and currently TDS class of satellites are also being developed by ISRO. And more predominantly, we would like to we have a very class of facilities to test these systems. Basically, we are working on plasma thrusters. Now we would like to know from our friends how things are being evolved in industries at different level on this advanced electric propulsion. To start with, I would like to request Mr. Sanket and other friends to introduce themselves before we go further.
Thank you, sir, for that. Hi, I'm Sanket Suman, co-founder and VP of RPO at Inspecity Space Labs. At Inspecity, we are developing cutting-edge technologies in space mobility. We are building robotic arms, propulsion subsystems, and rendezvous cameras, which allow spacecrafts to monitor, maneuver in space. Just a side note, our current propulsion systems are actually chemical in nature. So our focus is on building not hydrazine-based, but more on green propulsion systems. It's mostly based on nitrous oxide-based propulsion systems. We have been doing this research for about 4 years, and we hope to fly our first spacecraft in the next 6 months. Yeah.
Mr. Joshi.
Hello. Hi, my name is Manan Joshi. I am one of the co-founders at Thrustworks Dynetics. We are a liquid propulsion company. We design and develop liquid rocket engines for space applications, defense applications, and so forth. And we sell engines. So we build large engines. These are 2-ton class, 3-ton class systems, which has applications in dual-use technologies, ranging from hypersonics to defense tech. We have another range of thrusters called PAT. So we are one of the first companies in the world to build a passive acoustic thruster. So these are thrusters which do not require ignition and still can be used using kerosene and oxygen, or methane oxygen, or even hydrogen oxygen, but does not require any source of ignition. So these are resonant ignition systems that we have built, tested, fired, and now we are we have got we are now in works to transfer this technology from India to the US or the American companies. So propulsion tech in India, we have an amazing R&D infrastructure facilities. We have a lot of technical interest that we are building. We have amazing people and support from people at ISRO for helping us to develop this tech and building it in India and supplying to the world. That's what we're doing. Thank you.
Hello everybody, I'm Christopher Parmer, CEO and co-founder of Orbitt Space. We are based in Ahmedabad and we are building electric propulsion system for very low Earth orbit. This is a very new place to be and very challenging place to be. Already the low Earth orbit is getting huge amount of satellite numbers already planned, 12,000 of them already launched, and so many debris are already there, and because of the crowding people need to move to some new place, sustainable place, and that's where VLEO comes into picture. And when you come to VLEO, you are going into a difficult place, right, and you need to build a technology that is adapted to this new place. Electric propulsions are already said that is going to solve so many problems and very efficient technology for spacecraft, and that's what we are building. We are building radio frequency ion thruster for very low Earth orbit, and which is operated on air as a fuel. So till now people are using xenon, argon, krypton, but we have abundance of air molecules in 200-kilometer orbit, and if you collect those molecules as a fuel, you are going to increase the life of satellite in 200-kilometer. And 200-kilometer is a strategic place to be. Every country wants to be there in for their ISR need, right? And that's where we come into picture. We have already tested our first plasma thruster on nitrogen as a fuel, and already receive a thrust level. We are operating in space technical facility in Ahmedabad. We already built a cathode that works on air as a fuel, and we already got the performance matrices. So I guess in last 8 months only after operation, we got good technology development, and right now we are 20 people team. Previous to my starting this company, I was part of ISRO only for last 10 years in Space Application Center only, and we are building difficult technologies like traveling wave tube amplifier and the power systems like that. Thank you so much.
Okay, now I see a spectrum of activities in propulsion, starting with chemical propulsion to electric propulsion. Do you really feel electric propulsion, or how do you feel as an entrepreneur? How do you feel which propulsion is more comfortable to take over?
I'll have a very diplomatic answer for this. I think it's always going to be, I see the future being hybrid. So you need chemical to get, at least for, let's say, for ISR satellites, you need to orbit raise and achieve the operational orbits faster. You can't wait for weeks and days. But once you're there, you need to increase your lifetime using your electric propulsion systems. So in my opinion, a hybrid architecture is where the world is going towards. And even for LEO and even for GEO at the end of the day. Yeah.
Okay. What about Joshi? How do you feel about, from your point of perspective?
Okay, I have a bias. Ever since I was a kid, I was in love with liquid rocket systems. There's some beauty in complexity, and I do appreciate that beauty in liquid rocket systems. On the operational side, I think it's different with the ORs, whatever the operational requirements are. So generally for us, we have been pushing these systems for both defense and non-defense areas where you need to achieve certain velocities very fast. That's chemical rockets are really good. The problem comes in the turbo machinery side, the propellant side. What are you pushing it? Defense does not like cryogenic systems. So that's where you do innovation in the other segments and see what you can do. Our smaller thruster sides, this PAT, passive acoustic thrusters, and this has applications in this. We can't beat this electric or your efficiencies. There's no point over there. But as OTVs, requirement is OTVs. There is requirements in. The question is, Dawn has his new system is coming out 270 seconds. I think that's the max that is there. Can you build a system that is 300 seconds, which is storable? That's the question, and that's something that we hope that PAT solves that. Again, we are not a satellite propulsion company, so we're partnering with companies who work in that domain to give the PAT technology to them, and so that they can build on top of it. But depending on use cases, push the tech out.
Mr. Christopher.
So I'm very positive about electric propulsion because of the easiness that is bringing, the life that is bringing. Definitely comparison to chemical propulsion, the thrust level is very minuscule, but when it has to operate for longer duration, the ISP that electric propulsion is giving is from 2000 to nearly 5000, right? And this is the range of different thrusters. And when I see that the electric propulsion is not very new technology, it's been in the market since decades, and in Europe and US and multiple people has already replaced their chemical thrusters with electric propulsion. The ease of operation, you have power, abundant power from solar panel, and in VLEO also this is going to be the main technology, because in VLEO you require continuous thrust, right? It is not just orbit maintenance, it is a drag compensation, and for that you require a propulsion that can fire longer. And chemical propulsion, if you use the same technology, chemical propulsion in VLEO, you require a huge fuel tank. So electric propulsion technology is going to solve that problem for lower LEO problem.
Okay, but then this electric propulsion seems to be a little bit mass conservative. Thereby your launch cost also comes down. Is it not meaningful to provide the customers an option of going to an electric propulsion compared to chemical propulsion? Mr. Sanket.
Yeah, like I mentioned, electric is great for orbit raising, for orbit maintenance and for extended lifetime. It's mass conservative, but again, it has drawback of power. Especially out like where Christopher works, VLEO is amazing place where you can drag the air molecules, but the higher you go, the less dense the atmosphere gets. So you end up using krypton, xenon, these high pressure tanks, which is very, very hard to make it reliable and operate reliably over a long period of time. So, but no shade to electric propulsion, it has its place. But right now, as we see in the world, a lot of our missions are going to be rideshare, where you're deploying about 100, 200 satellites at the same time. You would need a very quick, agile system to separate out and go to an orbit where you're safe and you can measure and you can do your operations. That's one of the use cases for our chemical propulsion systems, which we're building for 1 Newton to 20 Newton thrusters. The second is the world is moving away from the globalized world to a more, let's say, multipolar world, if I may say. So for that, there's a lot of rise of inspection satellites, bodyguard satellites, where maneuverability becomes the essence of the satellite itself. That is where chemical propulsion systems can do quick maneuvers, either to dodge other objects or monitor other objects at the end of the day. So I would say again that electric propulsion is great for maintaining the orbits, especially for, let's say, if you have 1-ton class satellite, 2-ton class satellites, you don't want to put, like Christopher rightly pointed out, a big fuel tank. So you put a big, smaller tank for electric, but let's say for short-term operations, let's say orbit maneuvering or debris dodging, you would like to have a small chemical tank just in case.
Over to you, Mr. Joshi.
I would like to see an electric thruster which is 10 newtons and above. जब तक वो नहीं आता, our business is a bit safe on chemical side. but again, I think on a technology standpoint, there are two separate things. If there is in areas where electric exists, it's the requirement meet, there's no question. Perfect system, amazing. There are certain requirements where chemical works where electric doesn't, and that's where it has to grow. I think the pie is not small. This pie is massive and big and just increasing. Okay, we are talking about 1 billion satellites in space at some point. So even in space, to put it, there's an amazing amount of vertical that's there. My hope is with respect to newer propulsion tech, I think there's a lot of work happening in the US for even nuclear-based propulsion in space. I am not sure, maybe the exhaust gas will be plasma or ionized gas. So will that be your ionized electric or a nuclear electric or something like that? That's fun thing. So yeah, we see how it goes, but the pie is huge. There's a lot of room to play. There's a lot of tech to be given, exchanged, and developed.
So I feel it's the availability of the technology that is more important, and with whatever ingredients you have. Let us say we have electric propulsion, chemical propulsion tested TRL 9 and have heritage, and we have an electric propulsion still in test progress and not qualified yet. I would say the best choice is the chemical propulsion, because ultimately the mission and its operations matters most, and you have different trade-offs of technologies, right? When electric propulsion is ready and you have some maneuvers that still cannot be done by electric propulsion, right? You still need other part of chemical propulsion. So I see that it's a combination of these thrusters. It's not just one, doing all the works. I would say in some of the mission operations, we may also go with some of the chemical propulsion for NSSK or like that, right? But when it's more about the availability of the technology in your kitchen, what are available TRL 9 technology you have.
Okay, but basically the overall weight of the spacecraft goes up when you go for a chemical propulsion system, type of mobility, what you want to build into your spacecraft. But then here, electric propulsion doesn't have that weight. Then thereby your launch cost also is going to be advantageous if you want to go for such a spacecraft. That is one important thing what I look at, costing from entrepreneur perspective. Second one is the reusability. Assume your chemical, today we are in a situation where we don't have on-orbit refueling. Something like a aircraft on-orbit refueling, if it comes out, and then you feel whether when spacecrafts can be refueled on-orbit to extend its lifetime. Do you think electric propulsion will be advantageous to take it forward?
To refuel a gas in the orbit is going to be a challenge. I guess in Velio, what we are doing is again the refueling in orbit itself, right? And that is one part because your life is limited by the fuel you carry, and you need extended mission to extend the mission. You require fuel. The docking mechanism, and I feel that it's more easier when you have chemical, right? Because it does not have huge pressure difference. But when you have gas, your pressure compartment is very high pressurized, and docking and then delivering the fuel in that condition seems to be more complex.
What do you feel, Mr. Joshi, about this particular aspect compared to your chemical propulsion? If I want to refuel it, then I have to carry three fuels to on my spacecraft to get it refueled. It's going to be future thinking, but what is your
I love it.
thought about it?
No, I love it. Okay, so for us in this segment, so as we mentioned, we give the tech, we the passive acoustic tech for building on the space systems. So from that standpoint, in our case, it's both the system, your kerosene, as well as if you show pressurized oxygen, it's even if you store that. These are very something that storable systems. There's no cryo involved over here. So these are storable systems. You can store them at for a long time, and that has actually, if you're able to refuel it, you reuse it, and you again for orbit maneuvers and for OTVs, that segment, I think that's a good call and will be very beneficial for chemical systems.
Okay, Mr. Sanket, what is your opinion on this refueling and aspects?
So, like you mentioned, this is a very so this is something which we do at Inspacity. We are building our propulsion systems to be refueled in space, and that is what could be a differentiator going forward. Just having chemical only systems. So let's say even if you have a couple of spacecraft with xenon, you would still need a spacecraft to be able to go to the other spacecraft. Let's say a services spacecraft, and then the time the services spacecraft takes to go from point A to point B, you would rather do it with a chemical one. So, and then let's say if you're carrying a xenon tank, let's say if you have our propulsion system, which is nitrous oxide based, carrying an extra xenon tank, going from the mother xenon ship, this is very futuristic, then going to the client xenon ship, but you will still need some chemical propulsion satellite to do that. And once you go there, you replace and replenish the xenon. But what if the mothership itself has nitrous oxide or any other chemical chem-prop systems? Then your lifetime of your spacecrafts are not just a function of what they are carrying during launch, but they're also a function of what motherships and other service ships can provide. But I can see there is an advantage to electric. So because electric mothership will be much more smaller, but the refueling tech required to transfer 300 bars of xenon from one spacecraft to another spacecraft is a technology we are working on. Right now, we are trying to do it only for our chemical propulsion system because it's slightly more easier. But we just want to conquer that first. Once we do that, we will try to expand or collaborate with other Indian companies or foreign companies who have this tech to transfer other kinds of propellants as well.
Okay, but then what is that technology challenges you are facing if you think about electric propulsion, and what is that you look forward from the stakeholders in our country? In what way it can be of help to you?
I think the challenge I can speak for Inspacity, we face is to understand safety. So when we build propulsion systems in labs or building prototypes, we have some, let's say, standards we adhere to. But then going and building a prop system which is going to go to space, the safety requirements, the standards are much more higher because the risks are much more higher. Something goes wrong in the lab, you can still salvage it. Something goes wrong during launch or in orbit, it's God forbid something goes wrong. But so that's something I feel in space, LPSC, URSC, we have been talking to quite a few folks, and it has been amazing because a lot of engineers, scientists there have helped us out, give us very good direction on what we should take based on decades of experience within ISRO. I think it was currently done in a more informal way where we approach them, we talk to them. If we can formalize this much more better through InSpace, in which we can have regular technical sessions, from people working at cutting edge technology with LPSC, something just which helps us learn and grow with the public sector as well. That will be really great.
Okay. So Joshi, what is your difficulties you are facing in technology and simulation and innovations?
So our primary bread and butter are the large engines. We sell the large engines, 2-ton class, 3-ton class engines. We sell them, and that's how bread and butter works. In that aspect, our biggest challenge is with respect to the turbo machinery. Ultimately, that has been the big challenge for this. And building a turbo pump, we are actually pushing with a supersonic GG gas generator based turbo pump. So the efficiencies of that cycle is not as good as the staged combustion, but the complexity is very low. So these kind of system we are pushing it, and in that aspect, do a Google everyone. Do you have access to the top-notch turbo machinery, supersonic flow, turbine software? You don't. There's no access to it. So there's a lot of restrictions on top of that. So we had to sit and build those software infrastructure from scratch. And happy to say our first supersonic gas generator turbine got manufactured, undergoing testing at our own facilities in Pune, and we are even pushing forward for the entire stage to be built, turbo pump stage to be built here. But if you don't have the access of metallurgy, you don't have the access to software to design, and lastly, test facilities, that becomes the biggest. Test facilities you can build, but software, when you build software, there's like thousands of test data cycles or testing data comes together to build those softwares. That knowledge very difficult to get access to. So that has been our biggest challenge and one of the biggest bottlenecks.
So Christopher, specifically I would like to know this technology absorption in EPS. You are more working in that. How did you evolve now? What are the challenges you faced?
There are two challenges, main challenges in which we are building. It's the air breathing electric propulsion. So it's the air breathing part and electric propulsion part. Electric propulsion itself is a different set of challenge. It's a plasma thruster. It's a throttleable thruster, so you have to throttle the thruster based on the drag. We are dealing with very high voltages, around 2000 volts at 1 mm gap, and that is very difficult to, it's a very challenging part, where we are operating at 1 kilowatt power. Building those power system itself is very critical, and high voltage in space, more than 100 volt, everything is high voltage, right? So electronics power system is going to be the most important or more challenging part of this system, apart from thruster itself. Second part is air breathing part, and this is actually the newness in the technology, because till now you are carrying the fuel in the orbit, right, in your tank, but now you are totally dependent on the air or air molecules of this orbit. Your thruster works on certain pressures, right? It doesn't just operate like that. You provide power and it operates. You have to provide that pressure level into the chamber, and to create that pressure level, you have to understand the aerodynamics, and that's where the challenges of aerodynamics come into picture. Till now, nobody was, thinking of aerodynamics, because space was typically no aerodynamics. It's just a vacuum, right? But when you are talking about VLEO, you are actually talking about aerodynamics in rarefied regime, in molecular regime. My friend said that turbo pumps and something that takes, but there is a part in a molecular region, where compression and everything happens. So this is another level of challenge in terms of taking the air molecules and compressing it to the point where the plasma can ignite and create the thrust. So these two set of challenges that we are working. Third challenge is the orbit itself. The orbit is very dynamic. The drag changes, the density changes based on the solar flares and variation in the atmosphere. So you have to continuously adapt, and for that you have to provide a closed loop control, right? So you have to build a flight dynamics or flight software that continuously corrects this drag and provide the thrust and throttle the thruster. So this is something we are right now focusing on building, the thruster part, the power system, the air intake part, and the flight dynamic software.
Okay, but are you really finding any difficulty in sourcing this thruster materials? And how do you mitigate it?
All our thruster material right now, we are fabricating in India itself. I guess we didn't find any problem till now, because we are not directly using the full vacuum compatible materials as of now, the ceramics. We are definitely using metals that is space grade, but there are some ceramics we still need to import and then machine it to the precision that we require. So that is going to be one of the challenge, and only few vendors provide those type of materials or ceramics, right? Second part is the power system. Again, we are fully designing in-house, so we are not dependent on anybody. We have experience building very high voltage system in ISRO, like 7,000 to 10,000 volts. So we are building in-house, but the components again is a critical part. But we are going to use quartz component because this is very low Earth orbit. The radiation levels are not so much high, so it doesn't come under ITAR regulation. So that is what we are going to benefit it from.
How about miniaturization of the entire system compared to chemical propulsion? I want a plug and play system. Suppose if my system goes bad, I want to simply remove it, put back. How do you feel which system will be more comprehensive to attack with it? EPS system, electric propulsion system can do it, or you still feel chemical propulsion is easy to repair or maintain in on-orbit conditions?
I feel, and I'm not directly have experience in chemical propulsion. I guess my friend can comment on more on that. But electric propulsion, the integration part is tricky part. You're working on very high voltage system, high voltage assembly, RF power, and again mechanical and ceramic parts. So in terms of structural strengthening, everything is having a very well-defined processes. Until and unless you have well-defined process maintained, this particular electric propulsion needs more care than what I feel.
So Joshi, what is your thoughts on to that?
Miniaturization.
Miniaturization of propulsion systems.
Yeah. First of all, I am in awe of the world aerodynamic satellites. You guys are going on, it's amazing. On the miniaturization of the systems, we have actually done with our passive acoustic thrusters. We have done some good work on that. So we have like a 10 Newton thruster segment, which is it's less than this palm of my hand. That's the size. Without the tanks put in, it becomes a little bit bigger. So we have pushed for that. The same technology, weirdly the same technology, we had to miniaturize it even more for one of the defense applications. So that is going in a hand-in process. As the requirement comes, we can input more processes and we can shrink the sizes down. But ultimately it becomes a cost to benefit ratio. If we can miniaturize it a lot, क्या करना है आपको for us? If you have a gas inside, you make it high pressure. You go from SS to aluminum to titanium to COPV. You build the tanks and something like that. You can miniaturize it, but at certain point of times, the cost and economics just stop making sense. So that's not our call. That's for our users to tell us, okay, this is the price point that we need to be in, and our job then becomes, okay, this is the optimum size that we can provide in this particular cost range, and this is what we can do in this particular range, and this is how the system will look like. So at least up till now, that has been our journey, that has been our process, yeah, you can reduce it a lot, but again, cost ultimately. That's where you meet your imagination with reality somewhere in the middle.
Threshold.
Yeah.
Mr. Sanket, what is your understanding on this miniaturization? In fact, miniaturization is very much essential nowadays, as the space constraints are also a challenge for spacecraft manufacturers. What is your thought?
I 100% agree. And that's the, let's say, key thing. In older days, the spacecrafts used to be larger, let's say about a ton or just less than that. So chem prop systems were pretty easy to manufacture, build. So like Manan mentioned, one key thing we look at is our users. What are our customers telling us? So one of our customers came and told us, you know what, we want this proper system. We don't need a lot of delta V, but we need to put it on a CubeSat. So now, if I put a chem prop system in a CubeSat, I'll occupy a lot of volume. I can put payloads, but then the payload space becomes reduced a lot. So what the challenge they gave us is, can you push a bunch of things into the tuna wall block? So in CubeSats, just for the audience, there are typically some slots which go into the deployer. There's some extra space there, which is not part of the satellite, and you can put it outside. So that became our challenge. Okay, can we do that? And we were able to do that. So our first launch, which will be on a CubeSat, we miniaturized the thruster block, the walls, a bunch of things. I have a couple of folks from that team here as well. They pushed everything into the tuner ball, minus the tank. Because the tank, we wanted to keep it modular and make it user specific. If someone needs a 1U tank, which is about 10 cross 10 cross 10, great. If someone needs a larger tank, if they have a smaller payload, we can make it, let's say 2U, 20 cross 10 cross 10. So, and the lessons we learned during miniaturization has been phenomenal, because doing that out of India, finding the correct machinists, finding the correct people who can weld certain things is very, very hard. When you use something like electron beam welding, or you use a person to weld manually, the kind of results you get are not repeatable. So you need to figure out the processes, and it's a journey. So you figure it out, and once it's figured out, it's great. So now we are a little bit more confident that when we go to the small satellite sector, because that's where we are going next with our 6-star propulsion system for LEO and GEO satellites, we are more confident that it will work out. Because if we can make the chemprop system so small, like Manan said, fitting in the palm of my hand, then of course I can make it big. So I believe miniaturization is the way to go.
Then coming to pollution on orbit, what is your opinion with chemical propulsion or electric propulsion? What is that you feel will be really good?
That's a good question. So unfortunately, it's not in my hand. People are putting up satellites left and right.
Since you are a designer, what is that you want to see our environment is sustainable? And parallelly, you are an entrepreneur, you have to look at means to resolve such a problem. What is that you have in mind, or any challenges to still look at?
So we're looking at it in two aspects. One is debris removal, or small objects, or especially larger object removals, rocket bodies, and refueling. So extending lifetime of high value targets, either in GEO or LEO, or removing rocket bodies. So currently we have a big problem that a lot of either very small satellite CubeSats die in space after a few months, or you have these large rocket bodies from our launch vehicles just staying up there. So that's why in Inspecity we are developing robotics technologies where we can grab rocket bodies or small satellite depending on the user needs and move it and deorbit it. It's right now in works. We have not demonstrated it in space, but we have done a bunch of simulations. We have a microgravity test bed where we demonstrate let's say a floating robotic arm going and grabbing simulated targets and pushing it away. So I feel removing debris in space is going to be a big sector, but sometimes the government has to step in.
Yeah, but my question is not space debris.
I see.
My question is the debris left over by the propulsion systems. Assume there is a leftover propellant.
Okay.
Are you going to dispose it out of the orbit?
Yeah.
And that challenge is going to add cost to your company, isn't it?
Definitely.
That is what is my question.
Oh, okay. Sorry, I understood it wrong. So, yeah, so for chemical propulsion, the systems we are building at this moment, we plan to passivate it at the end of life so that it doesn't blow up, or in case there's a failure, crack propagation on the tanks or something like that. So there is no perfect solution. It's more of an operational solution we have, which you're borrowing from classical way of doing chem props. Is just passivate it at the end of life, or maybe middle of life if you are not using it. That's the reason I feel the hybrid architecture is great. So you have chemical prop system, you go to your orbit, you stay there, you passivate it completely, you are safe and you stay there forever. You use electric propulsion system to do orbit raising and maintenance, RAN correction and stuff like that.
So there electric is having better advantage.
Yes, definitely.
Accept. Yes, Mr. Joshi, what is your thoughts?
First of all, I would like to agree with him on the welder wala thing. Anyone, if here has a good welder who can do aerospace grade weld, please connect. So yeah, I weld myself, so I can understand the issue with this. I expertise in TIG welds especially. But yeah, on the chemical side, on this thing, uh, the exhaust is going to be there. Okay, you do whatever you want, the exhaust is going to be there. And what I think on the sub 10, this sub 10 meters and the particle size in that, that's where even the ablative coatings and some things they chip out in the chemical segment as well. When you go for thermal productions, they chip out and they have pollutions in that. And on this side, I think propellants like your peroxides and low carbon content propellants will actually be really great, because you have ultimately your water molecules coming out most. So that segment might help, but that's the max of the thought I have, because honestly speaking, I haven't given this the space debris people talk about. But on the question that you mentioned, the exhaust of the chemical propellants or these propellants, that how it is affecting space debris, that actually has stuck my mind that yeah, this is a new thing which we will have to think about.
Most important is with respect to your costing. How does it take care of your costing?
Exactly.
So we are mitigating both the problems in two different ways. First is the orbit that we are operating, VLEO itself has a property, it has the drag in it. So if your satellite is off defunct, it is not working, then it will be burned up in few weeks only. You don't require dedicated deorbiting mechanism. So this orbit itself does not retain debris, right? It's a debris-free orbit. So that is a very good part, because after your mission you are cleaning the orbit by itself and you are not creating more debris. Even collision happens, then it will clean up the orbit very fast right now. Second part is we are using air breathing. So again, air, nitrogen and oxygen is abundant in the atmosphere, but in upper part it is present in terms of molecules, and we are creating plasma out of it. And after the thrust, we are actually neutralizing that molecules also. So it's air again. So air intake, and we are just generating again air particles after the thrust. So fully sustainable, I would say. There is no yeah.
Okay, but then I want direct question. If I want to deliver 1 Newton thrust, which is cheaper, electric propulsion or chemical propulsion?
Chemical propulsion, definitely.
So you are still, can't you reduce the cost of electric propulsion? Where does the cost gets consumed more?
So for the specific application that we are using it, we require very small thrust, right? Millinewton thrust or 15 to 20 millinewton thrust. And for that application, I guess this particular propulsion system works best, right? But there are applications where you require more thrust, like in terms of 1 Newton or more than that. The amount of money put into electric propulsion is not going to compensate one small chemical thruster. Yeah.
Okay, is there any serious threats to electric propulsion? What is your thoughts?
Serious threats in terms of
Other advanced electric propulsion, like nuclear propulsion or space sails, solar sails, whatever has been thought out. Do you think they can supersede the advantages of electric propulsion?
No, I don't think so. So electric propulsion has a very nice niche with the 1000 to 5000 ISP and very small volume. It is fantastic. Solar sails and other, let's say, drag reduction devices are good, but practically implementing huge solar cells on spacecrafts will be very, very hard. Electric propulsion is well tested, thought out. One big challenge could be the type of propulsion, electric propulsion we have been using, which is pressurized, xenon, krypton, argon, mostly. We are going towards unpressurized electric propulsion systems. So there are a couple of companies out of Europe. They're building this solid propulsion systems based on, if I'm not wrong, field electric propulsion using solid iodine or indium, essentially, which need very, very micronewtons of thrust. But again, you need to fire for a very long time. So I think that advantage is going to be I think that's where the advantage even lies for this kind of propulsion system. Solid propulsion being used electrically But again, there is a small disadvantage to add to answer what Christopher was mentioning before when you asked, is the cost. So if you have an electric propulsion system, you always need a huge solar panel. You need a larger battery. So does the cost metric make sense there? Is the good question which we need to figure out for different classes of spacecraft. But for the advanced electric propulsion, I can see that the solid electric propulsions are giving a very, very good fight to the classical Krypton, Argon, Xenon prop systems.
Okay, Mr. Joshi, do you feel any threats to electric propulsion?
Nuclear.
Nothing.
Nuclear. Nuclear. I feel there is a lot of work happening in the nuclear segment, in the nuclear propulsion side. Especially there are some American companies which we were there, I think, in the space symposium. We visited them as well. They're doing some amazing work on that side. And nuclear has the energy, has the potential of combining the advantages of both chemical and electric side together. So that's something we see the future heading somewhere.
Christopher?
So there is a nuclear propulsion system which specifically uses electric only, but to generate that power, they are using nuclear power source. So your electric or solar panels using of bigger batteries is reduced by those type of technologies. I have largely not seen anything better right now than electric propulsion, and maybe it can come. But there are different types of electric propulsion coming up in the market, which is solving different problems like propellant storage, like neutralizer. You don't require neutralizer; your thruster itself neutralizes itself. Type of systems. But right now, it is just variant of electric propulsions only. Even nuclear thrusters are also just the powers. That is also electric propulsion. Yes, like helicon thrusters, gridded, number of type of electric propulsion system coming up. More than that, I have not seen any, which can disrupt the electric propulsion aspects. Looking for it.
But what about the availability of fluids like xenon, krypton? Do you think there will be unlimited supply in future?
So the very high purity of these gases, is basically the limitation is in the cathode, because it burns up the material and degrades the life of the cathode, and that is why the cost of this very high purity xenon is very high, right? Availability of those type of gases will limit such type of or subset of thrusters, but people are solving it innovatively, like iodine based thrusters, right? That doesn't require those type of high purity gases. Then other type of cathodes are coming up which do not require that high temperature or heater type of cathodes. They don't require, right? It just burns with RF power, so it doesn't corrode out those things. So yes, I mean, not using this high purity gas is going to be very commercially viable.
Okay. It's a nice discussion on the developments, what is going on in electric propulsion. Mr. Christopher right now working, and people on chemical propulsion also there. We had an interesting discussion. Any questions from audience before we wind up?
Thank you very much, honorable speakers. Gave so many detailed discussion, and it is benefited to the listener. I am Jigish Patel, ex-group director ISRO. Thank you very much, Mr. Venkatesh. I am ISRO Ahmedabad guy. My question is, nuclear is right now coining in the Western country. That's thing. Now the things are being coined that at space people are moving. There are agenda to go to the moon because they want to build the launch station at moon, because launching will be easier for the next further steps. So what are the effect of your propulsion system while we are launching the launch vehicle from the moon? First one. Second one, India is already announced our space station. So what are the system you can going to the sea for this space station? Thank you.
Yeah, I think for launching from the moon, launch vehicle concept doesn't really apply. You have mass drivers to do it. You have real launch mass drivers are more than enough to actually launch the systems. But to get to the moon, yeah, that's where again there's, I think, chemical is what you require to go for that. And there is a lot of work of SSA in cislunar orbit that is happening. Active work by the DoD, US DoD is also happening in that segment, and that's going to be a very amazing market. And especially we are looking to partner with companies for our PAT thrusters for that particular vertical. So yeah, we see that's something from Earth to the moon. PAT is something that we think that's going to be there. But for moon to up, Mars drivers are going to be there. I don't think you require a physical thruster on board.
Answer.
No, I agree with Manan on most of the points. And the chem-prop systems right now, the classical, let's say, high ISP and low mass is basically your LOX. So you have liquid oxygen, liquid hydrogen mixed together, and then you go up there. And there are a lot of other, I'm pretty sure the launch vehicle folks are working on it, and Manan's work also working on it. Going away from moon, apart from using mass drivers, you would also need some kind of, let's say, propulsion systems on top of it. Mostly again, chem propulsion systems, but I think nuclear propulsion becomes more attractive there. Because if you're launching from moon to, let's say, Mars or Jupiter or some other planets in the solar system, you need something which doesn't consume a lot of propellants. So electric propulsion, nuclear propulsion is very attractive for long duration missions where you need to slowly sail away beyond our asteroid belt and furthermore. For space station, I think you need chemical propulsion systems again because space station is going to be very large, very huge, like British multi-ton space station, where you need to do orbit maintenance. Doing with electric propulsion might be difficult. I'm not sure at this particular moment, but chemprop is the way ISS does it. They also use electric a little bit, but mostly it's chemprop doing the orbit raising and maintenance. So I can see the chemprop being the first solution, but if there is an electric propulsion system which can give multi-Newton thrusts with a good ISP of about 650, then I don't see a reason by 2040, when we have the Bharati Antariksh Station, why not use electric?
Thank you, sir. Thank you, all the participants here. Thank you, audience, for your patient hearing. Thank you very much.
A very warm thank you to our distinguished chair and esteemed panelists for a deeply technical and thought-provoking discussion on the future of space propulsion. I now request all the panelists and our esteemed chair to kindly come forward for a group photograph. Please give them a huge round of applause. We're honored to have you today.